Welcome back to AI.Code.Cast. You know, some coding challenges feel like puzzles, and today's is a perfect example. It's called Robot Bounded in Circle.
It's a classic. It really gets you thinking about how simple rules can lead to surprisingly complex outcomes.
Exactly. So imagine you've got a robot on an infinite plane. It starts at point 0, 0, 0, facing north. This robot only understands three instructions: G to move 1 unit forward, L to turn 90 degrees left, and R to turn 90 degrees right.
And the challenge is to figure out if, well, after repeating these instructions over and over again, will the robot stay trapped within some imaginary circle, or if it'll eventually wander off to infinity?
Right. It could spiral outwards, walk in a straight line, or even trace some crazy shape. Now, the materials you shared have a few different ways to crack this, and I'm curious to see how they work.
Absolutely. Before we dive into the elegant solutions, let's acknowledge the most straightforward approach: brute force.
Good old brute force.
Yeah.
It's not always pretty, but it gets the job done.
Exactly. In this case, we could simulate the robot's movements for a large number of steps and see what happens if we spot it revisiting the same coordinates or following a clear repeating pattern. We can be pretty sure it's bounded.
Yeah. But like you said, brute force isn't always the most efficient way. Imagine simulating millions of steps. It would take forever. And there might be some edge cases that are hard to catch that way. Plus, I bet there's a more elegant way to solve this, right?
There absolutely is. It's all about recognizing patterns and leveraging the problem structure. One of the solutions you provided does just that. It's called optimized circular path detection, and it hinges on a really neat observation.
Okay, I'm all ears.
So instead of simulating the robot for ages, what if we just looked at what happens after it goes through the instructions once? That's one full cycle.
I'm intrigued. How does just one cycle help us?
Here's the key insight. After one cycle, there are only two scenarios where we can guarantee the robot is bounded.
Whoa, let me guess. One is if it ends up right back at its starting point,
Yeah.
0, 0, 0, 0. But what's the other one?
You got it. The first one is indeed returning to the origin. The second is a bit trickier. But think about this. What if the robot isn't facing north after one cycle?
I wouldn't have thought of that. Why does not facing north mean it's bounded?
Because if it's not facing north, it means its direction has changed from the initial facing north state. And since these instructions repeat forever, any consistent change in direction forces the robot into a looping path. Now, that loop might not be centered perfectly around the origin, but it will definitely be confined.
Ah, I see. It's like it's caught in a dance, always turning and shifting, but ultimately staying within the same area. That's a lot more efficient than watching the robot wander for hours in a simulation. But before we move on, can you give an analogy for the second scenario, where the robot is bounded even when it does not end up at the origin?
Sure. Think of it like a planet orbiting a star. The path might be elliptical, not a perfect circle centered on the star, but the planet is still bound within a specific region due to gravity. In our robot's case, the change in direction acts like that gravitational pull, keeping it within a certain boundary, even if it doesn't return to the starting point.
Okay. Now, that makes sense. So to use this method, we'd simulate the robot for just one cycle of instructions. If it ends up back at the origin or isn't facing north, we know it's bounded. What if neither of those is true?
If neither is true after one cycle, it means the robot ended up at a different location and is facing north. This implies a consistent movement in a single direction, meaning it's going to keep moving in that direction forever and won't be bounded.
That makes perfect sense. So we've got this clever way to figure out if our robot is trapped, but we haven't talked about how to actually put this into code. What would that look like?
It's actually pretty straightforward. You'd initialize your robot's position at 0, 0, and its direction to north. Then you'd go through each instruction in the string. If it's G, you update the position based on the current direction.
Right, so if it's facing east, G would add 1 to its x-coordinate.
Exactly. If it's L or R, you just update the direction. Once you've processed the entire instruction string, you just check the robot's final position and direction.
And that tells us everything we need to know. This optimized circular path detection is way more elegant than brute force. Seems pretty efficient too, right?
It is. The time complexity is ON, where N is the length of the instruction string. We only go through the instructions once. And since we're just storing the robot's position and direction, the space complexity is O1, meaning we're using a constant amount of memory, no matter how long the instructions get.
Okay. I'm really liking this approach. It's efficient. And it leverages the problem structure in a smart way. But you mentioned other solutions in the materials. Is there another way we could tackle this?
Absolutely. There's another approach called the state machine. That takes a slightly different perspective. It shifts the focus from individual movements to the robot's overall state.
Now that you mention it, I do remember seeing that term, but I'm a little fuzzy on what state means in this context. It sounds a bit abstract. Could you break it down for me, and maybe for our listeners who might be in the same boat?
Of course. In this case, the state is like a snapshot of the robot at any given moment. It captures both its position, meaning its x and y coordinates, and its direction, north, south, east, or west. So it's not just where the robot is, but also which way it's pointing.
Okay, I think I'm starting to get it. So instead of just looking at individual movements like go forward 1 unit, we're thinking about how each instruction changes the robot's overall state.
You got it. Each instruction, G, L, or R, acts like a rule that transforms the robot's current state into a new state.
Interesting. I'm guessing this state machine approach gives us a more structured way to analyze the robot's behavior.
Exactly. It allows us to think about the problem in terms of transitions between these states. And just like with the optimized circular path detection method, we can use this information to figure out if the robot's movement will eventually form a loop.
This is getting really fascinating. Can you walk me through how we would actually implement this state machine approach?
Sure. We start off just like before, initializing the robot state to position 0, 0, and facing north. Then we process each instruction in the input string.
And how do we update the state based on the instruction?
Well, let's say the current state is 1 Rensu facing east. If the instruction is G, we would update the state to 2, 2, still facing east. But if the instruction is L, the state would change to 2 facing north, because the robot would turn left.
Okay, so each instruction have a very specific way of changing the robot's state. So how do we know when the robot is bounded using this approach? Is it the same logic as the previous method?
It's very similar. The key here is to analyze the robot's state after one complete cycle of the instructions. Just like before, if the robot ends up back in its initial state, both in terms of position and direction, we know it's bounded.
Okay, so that part makes sense. But what about the second condition, where the robot isn't facing north? Does that still apply in the state machine approach?
It does, even in this approach. If the robot's direction isn't north after one cycle, and the instructions keep repeating, it's guaranteed to loop, even if that loop doesn't perfectly center around the origin.
I'm starting to see how this state machine idea works. It's almost like we're creating a map of all the possible states the robot can be in, and then we're watching how it moves between those states. And by analyzing those transitions, we can predict whether it will ultimately be bounded or not.
Exactly. And the best part is that this approach can be applied to all sorts of problems, not just robots moving on a grid. Anytime you have a system that changes state based on certain rules, you can use a state machine to model and analyze its behavior.
Okay, now this is really cool. So we've got two really clever ways to figure out if our robot is bounded. Optimized circular path detection and state machine. Both seem pretty efficient too, right?
Absolutely. Both methods have a time complexity of ON, as we process the instructions only once, and they both have a space complexity of O1, because we're only storing the robot's current state, which requires a fixed amount of memory.
So they both have the same time and space complexity. Are there any trade-offs between the two, or are they basically interchangeable? Which one would you prefer, and why?
It really comes down to personal preference and how comfortable you are with the concept of state machines. Optimized circular path detection might feel a bit easier to grasp initially because it's more directly tied to the robot's movement on the grid.
That makes sense. But the state machine approach, while maybe a bit more abstract, seems like a more powerful and general tool to have in your coding toolbox.
Exactly. It encourages you to think about systems and their transitions, which is valuable in many programming scenarios. But, you know, we have one more approach in your materials that I think you'll find quite interesting.
Ooh, another approach. Got me really curious now. What's this third method all about?
This one uses a bit more math. Get ready for some vectors. This one uses a bit more math. Get ready for some vectors.
Vectors. Okay, I remember those from way back in math class. They always seems kind of cool, but also a bit intimidating. Like arrows pointing to, well, something. How do they apply to our robot problem?
That's a great way to think about them, arrows pointing somewhere. And in this case, they're a really elegant way to represent both the robot's position and its direction at the same time.
Hold on, how can a single arrow show both of those things?
Think of it this way. The arrow's starting point is the robot's position on the grid. So if the robot is at 2 and 3, the tail of the arrow would be at that point. Now, the arrow's direction and length tell us which way the robot is facing and how far it would move if it took a step forward.
Okay, I think I'm visualizing it. So if the robot is facing east, the arrow would point to the right horizontally, and if it was facing south, the arrow would point straight down.
Exactly. So instead of keeping track of the robot's x and y coordinates separately and then its directions separately, we can combine it all into a single vector. Pretty neat, huh?
It is. It's like we're packing more information into a single piece of data. So how does this vector representation help us solve the bounded circle problem?
Well, remember how in the other methods we were updating the robot's position and direction based on the instructions? We can do the same thing with vectors, just using a bit of vector math.
Okay, I'm following so far. But how do we actually apply G, L, and R instructions to a vector?
Let's start with G for moving forward. That's the easiest one. Since the direction vector already tells us where the robot is headed to move it forward, we simply add the direction vector to the position vector.
Ah, so we're essentially shifting the starting point of the arrow by the length and direction of the arrow itself.
Exactly. Now for L and R, which are rotations, we use specific formulas from vector math to rotate the direction vector. It's a bit more technical, but the basic idea is that we're changing the arrow's direction without changing its length.
So we're basically pivoting the arrow around its starting point, either clockwise for R or counterclockwise for L.
You got it. And these formulas are standard in vector math, so you don't have to reinvent the wheel. They take care of the trigonometry behind the scenes.
I'm starting to see the power of this vector approach. It feels more concise somehow.
It is. And just like with the other methods, we analyze the robot's final position and direction after one cycle of instructions. If the position vector ends up back at 0, 0, or if the direction vector is different from its initial value representing facing north, we know the robot is bounded.
Okay, so the logic for determining boundedness is consistent across all three approaches. But it seems like this vector method is particularly elegant, at least in terms of how it represents the robot's movement.
It definitely is. And beyond its elegance, it also highlights an important principle in problem solving. Sometimes finding the right representation of the data can drastically simplify things. In this case, switching from separate coordinates and direction to a single vector makes the movements and rotations much easier to handle mathematically.
That's a fantastic point. It's like we're finding a language that's perfectly suited to describe the problem, making the solution flow more naturally. It reminds me of how choosing the right data structure can make all the difference in writing efficient code. So let's talk about efficiency. How does the vector approach compare to the others in terms of time and space complexity?
It's right in line with the other two.
Yeah.
The time complexity is still O(n) because we process each instruction once, and the space complexity is O(1) because we're only storing a few vectors regardless of the length of the instructions.
So all three methods are equally efficient.
That's impressive.
Seems like there's no clear winner here. The best approach might depend on the individual coder's preference or the specific context of the problem.
That's exactly right. Each approach has its strengths and provides a different way of thinking about the problem. Optimized circular path detection is very intuitive. State machine offers a structured way to model the robot's behavior, and vector representation brings in the elegance of math. It's like having a toolbox full of different tools, and the best one to use depends on the task at hand.
That's a great analogy. It's awesome how this one coding challenge has given us so many different perspectives and even reminded us of some broader problem-solving
Oh,
principles.
absolutely. But you know what? There's something else I've been wondering about. What if we changed the rules of the game a little?
Ooh, I like where this is going. What kind of rule change are you thinking of?
Well, what if the G instruction didn't always mean move one unit forward? What if it could move the robot a variable distance or even in a different direction altogether? How would that change things?
That's a really interesting question. It would definitely make the problem more complex.
Mm.
But I'm curious, could we still apply the principles we've learned so far, or would we need entirely new approaches?
That's a great question for us to explore. I think we could still leverage some of the core ideas, but we definitely need to adapt our strategies.
Yeah, our neat little tricks for checking the robot's position and direction after one cycle might not cut it anymore if things get more unpredictable.
Exactly. If the G instruction could move the robot different distances, simply checking if it returns to 0, 0 wouldn't be enough.
Hmm.
Imagine the instructions are GGR, and each G moves the robot 2 units forward. After one cycle, it would be at 4, not the origin, but it'd still be bounded in a circle.
Ah, I see. So we need a way to figure out the overall range of the robot's movement, not just its final position.
Right. We might need to track the minimum and maximum X and Y coordinates it reaches during that cycle. That would give us a better sense of the area it's confined to.
Okay, that makes sense.
Mm.
What about if the turns weren't always 90 degrees? Things could get really wild then.
Absolutely. That's where our vector approach could really shine. Instead of simple 90-degree rotations, we'd need to use trigonometry to calculate the new direction vector after each turn. We'd be working with sines and cosines to figure out the exact x and y components of the vector.
Ooh, that sounds like it would take some serious math skills. But I bet it would be super satisfying to get it working.
It would, and it would showcase the power of vectors for representing more complex movements.
So even with these trickier rules, the right tools and techniques can still help us solve the problem. It's just a matter of adapting our thinking and being ready to embrace a little more complexity.
I love that takeaway. This robot bounded in circle problem is a perfect example of how coding challenges can evolve. You start with a basic set of rules, but then you can tweak them, add variations, and discover a whole new layer of challenges and insights.
It's like we're pushing the boundaries of the problem. And in doing so, we're also expanding our own understanding of algorithms and problem solving. We've gone from simple simulations to state machines to vectors, and now we're even hinting at trigonometry and more dynamic movements.
And who knows what other variations people might come up with. Maybe the robot could have sensors, or it could interact with its environment. The possibilities are endless.
Exactly. It's a great reminder that learning to code isn't just about memorizing syntax. It's about developing a mindset of problem-solving, creativity, and adaptability. It's about being able to take a challenge, break it down, and find elegant solutions even when the rules of the game keep changing.
Couldn't have said it better myself. Well, folks, I think we've reached the end of our deep dive into the robot bounded in circle problem. We've explored multiple solutions, analyzed their efficiency, and even contemplated some exciting variations. Hopefully you found this episode informative and inspiring.
Absolutely. A huge thanks to our listeners for joining us on this journey. And remember, whether you're a seasoned coder or just starting out, keep experimenting, keep challenging yourself, and most importantly, keep having fun with algorithms. Until next time, happy coding.